we will continue with the kinetics that we began in the previous class, starting from the cause to the effect, and we will look at certain parallels between rotational motion and translational motion, in particular for 2D cases, which is kind of a specialization of what we were looking at in the previous class. Though we did touch upon 2D once in a while, most of the things that we were talking about in the previous class was related to 3D, so very general stuff. So this will be a specialized case of that. And in the translational motion, of course, the cause is the force and the effect is displacement. In between you had the connectivity in terms of the acceleration and the velocity. So it is a four-way connection that you had. And we had something which was kind of retarding this in some sense, which is an inertial effect, which is self-contained in this connection between the force and the acceleration, which is your mass. The more the mass, the more the inertial nature, so that kind of for the same force you have lesser acceleration, right? So that's the whole idea of the mass. And these of course were just time derivatives, and for this to work these had to be in the inertial frames of reference, any inertial frame of reference. Okay, so now what we are doing now, this is all thanks to Newton. Now with Euler, what we are doing is, instead of F you have the m, instead of A you have the angular acceleration alpha, instead of velocity you have the angular velocity omega. I heard most of you calling this as W, so let's avoid doing that. So it's more kind of rounded, and you typically call this omega, the Greek letter. And then of course the displacement is an angular displacement that you have there. And more appropriately, the connection now is called inertial, and the moment of inertia comes into picture over here. Truly speaking, this is actually a matrix. It's a 3x3 matrix that you would have in a Cartesian coordinate system involving the x, y, and z directions, and also couplings between them, what we call as the products of inertia. But for most problems that we'll be looking at, we'll be concentrating one of those diagonal elements, so that should kind of work, right? So then coming to the these of course once again are the same inertial differentiations that you have. So it's just the first order derivative, a linear operator that you have over there. Okay, so it is this analogy which we'll try to look at, and doesn't work in such a clear manner when you're talking of 3D because of the involvement of multiple couplings, etc. But you can see that parallel much more clearly when we are dealing with this. Then there's also a connection that we brought about between these two guys over here, M and V, and we call that the translational momentum L. Beware that a lot of books will use P for this, and L will actually be used for angular momentum, but we use the notation L for the translational momentum and H for the angular momentum. H is a very commonly used word for the angular momentum. So this is essentially the product of these two guys over here. So it's equivalent to that, and you have this angular velocity, right? So now it's very important to note which of these are vectors. So pretty much all of them are vectors over here, and you have your momenta are vectors as well, both the translational as well as the angular momenta. Okay, so now what we are looking at is in terms of extending the Newton's laws to the rotational motion, and we already saw those two laws in the 3D case, the first and second laws of Euler, and now we will look at the first law is kind of very similar. It's just an integration over the particles that the body is composed of. So we just concentrated all of the mass at the center of mass of the body, and then we dealt with it as particles, just like how Newton did. What is more novel or new is essentially the second law, where you bring in all of these new concepts that relatively new concepts that were introduced in the previous class itself, right? So now the notations that I used over there and on the whiteboard are one and the same. Theta is your angular displacement, omega is your angular velocity, and alpha is your angular acceleration, and that's essentially what we would like to express the second law in terms of. So it's an alternate way of doing it, which is simpler for dealing with certain problems in a more direct implementation. Okay. So first of all, what do we mean by 3D and 2D? So essentially 3D means that the number of independent variables in space is essentially 3, and in the case of 2D it is 2. So apart from time, of course, being an independent variable, so that's essentially what you're looking at. So in other words, if without loss of generality, we can always choose the 2D plane such that the z-axis is perpendicular to it, and that's k hat. And so once you have k hat as chosen direction for perpendicular to the plane unit vector, becomes k hat, and therefore once again the sum of all the external moments that are acting should be equal to the time rate of change of the angular momentum, which is h that you have over here. We also saw that this kind of a simplification is not always possible because of the very definition of h that we had. If you recollect, it is just defined as the cross product of the position vector of that particular, so it's essentially a cross product between whatever you're looking at in terms of each element, or if you're looking at concentrating everything at the center of mass for a set of particles, then this becomes from the point about which you are taking the moment to the point of either the infinitesimal mass or the center of mass. If it's infinitesimal mass, you of course have to integrate in order to get that. So this is essentially what we were having, and so if you look at in terms of the time rate of change that we were looking at, just like the time rate of change of L was giving you F. So this is again another connection which I forgot to mention over here. The FL connection is again in terms of I d by dt, just like the connections between the acceleration velocity and displacement as well. So similarly here you have a connection between h and m in terms of an I d by dt, but this does not always hold, because now if you take the definition of h and I take an I d by dt of this, which is I d by dt of this quantity, just like the time derivative or any derivative of any product, it's going of uv, let us say it's going to be u dv plus v du. So you're going to have the derivative of this and then crossed with this, and then this crossed with the derivative of that time derivative. And what we actually require for the simplest case is only for r cross dl by dt to remain. The other one will be a kind of a velocity, which is dr by dt crossed with L, and that's usually a troublesome term if you're choosing any arbitrary point about which you're defining this angular momentum. So unlike translational momentum, which is a property instantaneously of the motion itself, h is not. It also depends upon the choice of the point about which you're taking the moment. So that choice has to be made wisely so that you don't end up with additional terms unnecessarily in the derivation. So that most important additional term that you would be getting is when I take the d by dt of this, I will not only get an r cross L, which L dot, which I'm quite happy with, because I can just call that as, because your L dot is nothing but your force, and therefore this just becomes r cross f, which is nothing but your torque or moment m. On the other hand, the other term that you're going to get is essentially an r dot, of course, from the point about which you're taking the moment to whichever point is of interest over there, either the center of mass or the infinitesimal mass, and this is going to be an r dot cross L, and this is usually a kind of a troublesome term to deal with, and we try to see special cases where this goes to 0. In fact, we introduced that in the 3D case already. We talked about it either being the point about which you're taking the moment either to be the center of mass or anything which is inertially fixed, okay? And in 2D case, we have many such points because you have just an axis k hat, and every point on that axis is common between an inertial frame of reference and the rigid body, because its rigid body is essentially rotating about that. So that's essentially 2D. So it's very easy to choose that particular point and therefore drop off this second term entirely. This goes to 0 and you are living with only this. So it's kind of analogous to the translational problem now, where we were talking about the force being the time rate of change of your momentum, that the time rate of change of momentum over here, or translational momentum. Similarly, your moment here, or torque, if you would like to call it, is essentially the initial time rate of change of your angular momentum, if that point is one of these special choices, right? So keeping that in mind, we are choosing, let's say in this example, the center of mass as the point about which you're taking the moments. So therefore this becomes mc on the right hand side, just becomes your angular momentum, which in this case, because it's a 2D problem, there's a rotation only one direction, which is the k hat direction, and your angular momentum will be parallel to your omega. So in other words, h and so your h and omega will be parallel to each other, and both will have only a k hat component, no I hat or j hat component, right? So and that component of course is very similar to how you're looking at in terms of translational momentum. You look at mass into velocity. Here you're looking at a moment of inertia, the corresponding appropriate moment of inertia times the angular velocity or angular speed, so magnitude of the angular velocity. So all of which are obviously in the z direction. So the moment of inertia is about the zz. So it's in other words, the a diagonal term in the inertia matrix, and it's important to specify the superscript there as well about which point you're taking the moment of inertia. And similarly, your angular speed, omega z, is the z component of the angular velocity, only non-zero component that you have. So now only xy plane forces. So only xy planar forces, because you see that it's a 2D problem, so there are no forces in the z direction and no motion in the z direction as well in terms of translation. But on the other hand, moment has only a z component, doesn't have an x and y component, and therefore whenever there's only one component, just like in rectilinear motion, if you recollect, we had only one direction translational motion, we could just use scalar equations. Vector equations were an overkill, though you could use it in a generalized sense, but essentially it simplifies the problem, and you have just one component. You can as well deal with it as if they are scalar equations. It's very similar to in your statics course also. You would have looked at equilibrium equations, where you instead of the vector f equal to 0, you put fx equal to 0, fy equal to 0, fz equal to 0, where fx, fy and fz are the resultants in the x, y and z directions of the force, total force, external force acting on the system. So similarly here, when you have just one component, which is a z component, mz, you just have to take that equal to 0. So you might as well deal with a scalar equation. So the only difference between the green and the orange that you have over here is that you have reduced the vector equation to a scalar equation that you see over there, right? So you have dropped that k hat in the denominator, sorry, k hat in the right hand side, and this is what you have. And also, just like in most problems already with translation, we were saying that the mass doesn't change, only velocity changes, and therefore just like how we could reduce the time rate of change of translational momentum to just mass times acceleration for the force, here just moment of inertia times the angular acceleration. This is d by dt of omega z, which we will call as alpha z, and it's the only alpha that is alpha non-zero alpha component that is there, right? So we might as well drop the z, understanding that we have introduced whichever plane the 2D motion is taking place to be the xy plane, and therefore perpendicular to that is a z plane, and it's understood that all of these are with respect to z. So as far as thetas and omegas alphas are concerned, we drop the z over there. You could actually drop the z over here and the other places as well, as long as it is understood and it's made very clear up front, so that you don't carry around all of these additional baggage, right? So this is the simple state of Euler's second law as far as the 2D motion is concerned. Makes it very, very easy and simple to apply to a lot of problems, okay? And remember that this troublesome term was got dropped off because we chose the point about which you're taking the moment of the angular momentum as c, and that's why this simplification has happened, right? Now 2D rigid bodies, you see the rotational dynamic equation what we have just showed on this slide, because we are dealing only with Euler's second law, not the first law, is essentially a scalar equation. But don't forget that the translational dynamics for this problem will continue to be a vector equation, because it will involve both x and y components of forces, x and y components of velocities, translational velocities that is, and the translational accelerations also. So all of these quantities v, u, a, etc. will not of course be three-dimensional vectors anymore, but they will be two-dimensional vectors, and so the typical vector equations and the rules for vectors will kind of apply there, including of course the way you take derivatives, etc. Here it becomes much simpler in terms of how you take the derivatives. So you just have a theta dot for the omega and theta double dot for alpha. It's quite straightforward, okay? So now let's get back to 3D bodies, 3D rigid bodies, and this time as far as the angular momentum is concerned, we want to take it about any point of the rigid body, okay? So not the center of mass, not necessarily an axis of rotation. In this case, of course, the axis of rotation may not be a constant k hat. It could keep changing as the motion occurs. It could be in different directions, could be of different values. But what we are looking at is in terms of as far as the restriction is concerned in this slide, we are only restricting it to be any point which is associated with that rigid body. So when we say any point of the rigid body, it could be either on the surface of the rigid body, it could be within the rigid body. If it's, let's say, a hollow sphere, for example, it could be even in empty space within that, or it could even be completely outside the element. But essentially it is kind of moving along with the rigid body. Whenever the rigid body rotates, the line joining the center of mass of the rigid body and that particular point rotates in the same manner by the same amount in the same direction. So essentially you are associating that point with the rigid body in the sense that that point relative to the rigid body remains fixed, okay? But it's not necessarily an inertially fixed point. That is something to be remembered, okay? This is the final result that we are going to get because of this, which is of course going to have the term that you will always get, which is your second term over here. In a lot of the work that we did with translation, especially motion around a circle or a circular arc, anything which is not straight line for that matter, we had the centripetal acceleration which involved an omega squared with an r. But remember that this looks kind of similar to that, but it's a single omega with an r squared kind of a thing. So it's not the centripetal acceleration, it's quite different from that. It's part of the angular momentum, which is going to be the major part which is going to stick around with you for almost all your problems. So essentially it's this part that we were talking about over here, okay? Whereas the problem part remains in this particular case because we are choosing it not as the center of mass of the body, nor an inertially fixed point, but any particular point of the rigid body in, on, or with respect to the rigid body it's fixed. That kind of a point we are looking at. We're calling that point as P, and that point P, its velocity, the pre-cross product with the position vector will remain.
Also capital P, or is that different to the other P?
This. Oh yeah, I'm sorry. This should be P. Yeah, you're right.
In C,
yeah.
using C as center of mass in example, but this time is it just the center? Is it still the center?
No, the C is still the center of mass. Yeah. Glad you asked. Yeah. So this should be big P. I think everywhere else it's fine. And Q, of course, is the infinitesimal element dq, dm. It will keep changing in this integration. So that's what you're essentially integrating with respect to. Okay. Yeah. So we will kind of stick to this particular notation as far as unless and until I change it, I'll not mention. But C is the center of mass and Q is the location of the infinitesimal mass element, and P is any arbitrary point which we need to define for that particular slide. Okay. So as always, I'm just giving you the end result, what we would like to get to in this particular slide in orange or red, and then we'll start with something green, and then the steps in between we'll use an yellow font, and then we will see how we get there, right? So the conditions are very clear that it's fixed to the rigid body. So we have something associated with this because it's a point on the rigid body, that P, about which you're taking the angular momentum. So therefore, of course, this is always true, but we will have some simplification going forward. But essentially, the mass times the velocity is your momentum, which is an infinitesimal momentum of the infinitesimal mass element, and its position is at point Q, and we want the position vector from the point about which you're taking the angular momentum. So that position vector is what you're pre-crossing the infinitesimal momentum with, and you're integrating over the entire rigid body to get the angular momentum of the rigid body about that chosen point P. Okay, Q is, as I said, point in dm of Rb. Okay, because infinitesimal elements, essentially you're shrinking it eventually in the limit to size 0, which essentially means that is the point you're shrinking it towards. Now the velocity equation that you used almost for every problem that you solved in the previous assignment, any 2 points which are fixed on the rigid body, you know that they are kind of related to each other in terms of the cross product being the only difference between them. That cross product is of the angular velocity of the rigid body crossed with the position vector from the point whose information we know to the point whose information we do not know. Therefore, P to Q, not Q to P. Okay. So if you for some reason interchange that, this of course should become a negative sign, or R should come before and omega should come later, so that you maintain the consistency of this equation, right? So now the reason why this is valid is because both P and Q are points which are fixed to the rigid body, and therefore Q being any arbitrary point of the rigid body, and P of course being the chosen point about which you're taking the moment. So that's essentially what you have here. So this expression we want to substitute for the velocity over here, because the velocity has come as part of the translational momentum. So I want to substitute for the VQ here. So I'll have, instead of one term, we'll have 2 terms, and we'll have to see what happens to either of them, right? So now when you take that particular cross product, you see that so you just substituted Vp plus omega cross R PQ over here, and you're pre-cross multiplying with rpq over there. Now, therefore, it's going to give you two terms. This is the term which you're going to be burdened with throughout the course, the rest of the course, whereas the first term may sometimes go to 0. In this case, it doesn't necessarily go to 0 because of the way P is chosen, but you essentially have this kind of a cross product where you have R from P to C, a point P fixed on the rigid body, but not necessarily its center of mass, but to the center of mass, and then crossed with Vp. Once again, yeah, this is the same thing, same mistake that we had seen earlier. So this is if you and you can see special cases of what we had looked at already. For example, if P happens to be the center of mass, then this becomes RCC, which is 0, and so essentially goes to 0, and so on and so forth. If it's an inertial point, then you know that Vp is going to be going to 0 because you don't have any acceleration associated with that, and so that is and it's a part of the body as well. So you will see that some of the results that we had got earlier become special cases of this. So next thing that we would like to look at again, and another expression for the angular momentum, which is just the, if you remember what we saw at the end of the last slide, it's just the second term of the last slide. In other words, the first term is dropping off, and this is for the case where you have any inertially fixed point of the rigid body, and this is the example that some of you gave last class in terms of the axis of rotation, or any point on the axis of rotation. When you have any point on the axis of rotation, you would see that that is a point which is fixed on the body. It's also a point which is inertially fixed, and therefore it satisfies this condition that we are starting off with in terms of what we want to derive an expression of the angular momentum for, right? So recollect this general expression that we already had, including both the terms. Now we have to show that for this special case that the first term actually drops off. Any idea why does it drop off over here? For an inertially fixed point of the rigid body. It need not be on the axis of rotation, that's one example, but any inertially fixed point of the rigid body, this has to happen, that the first term drops off. So what is about the first term that makes this go to 0?
The VP, right?
Yeah.
The VP.
VP, yeah.
Because it's
Yeah.
not accelerating something.
Yeah, yeah, yeah,
But, well, it's just velocity, they're not
Yeah.
changing velocity.
okay, anyway. So the point is fixed on both the rigid body and the inertial frame of reference essentially means that it is 0, because if it's fixed on the rigid body and it's fixed in the inertial frame of reference, then obviously it's not only that for every point on the inertial frame you're right that acceleration is 0, but once it is common to both the body and the inertial frame of reference, then your velocity has to go to 0. Okay. So that's essentially because of that Vp equal to 0, as you rightly pointed out, and this is what we call in 3 dimensions as a pivot point. So it's about the point about which the rotation motion takes place eventually. So that's called your pivot point. So it could essentially be, let's say I have a body which is kind of pinned at one particular point, and then it's essentially free to revolve about that. So this is a 3D motion. It can not necessarily occurring in a plane. It could be about any direction, and that's essentially a pivot point. And the same thing can be specialized to 2D, where now instead of just a single pivot point, you will now have an axis of rotation, essentially the loci of that fixed axis. Okay, so all points of that fixed axis, any one of those points could be this chosen point P, and once again Vp will go to 0, and therefore the first term will drop off, and you're left with this term involving a square in the position vector dimension and just one as a part of the angular velocity, and then of course an integration over dm, which of course has the units of the angular momentum that we are interested in. Next, we want to do this now for 2D, but about any point. Okay, so again we are not restricting the point in any sense to be either the center of mass. So we are not restricting this point in any sense, but the motion of the rigid body we are restricting to 2D, which is essentially we are choosing the k hat direction to be one about which the rotation takes place, and perpendicular to that about on which the translation entirely takes place. So once we do that, the final result that we will get in terms of the angular momentum will be both those terms kind of remaining, the first term and the second term, but the second term will get simplified quite a bit because there's only one angular velocity component which is non-zero, which is your omega z, so that alone remains, but the first term is still there, complicating our lives as far as the further implementation is concerned, okay, because of the fact that the choice here is an arbitrary point, any point, by which I mean any arbitrary point, okay. Now as far as IZZ is concerned, that same definition that we introduced for 3D holds here as well, so that it's about point P, therefore the position vector has to be from P, about whichever point about which you're getting this, to the arbitrary material point, and we have to integrate over all of the material points over the entire rigid body, which is your integration of dm, which could many a times have to be replaced by rho times dv, the mass density times the volume element, right. So now let's see how we get to this. The only simplification of course is going to happen with the second term, and this is something we were familiar with, the Euler's second law, the very first slide what we introduced in today's class, right. So this is the general expression, always valid for 3D motion about any point P, and now always that will be our starting point, that's why I put it in green, and what our destination is in red, and the in between steps will be in yellow. So for any point P of the 2D rigid body, you will have the position vector going from P to Q, because it's a two-dimensional motion, the z component is not there, and you just have the I hat and j hat terms, xpq and ypq coming up there, and then you have your angular velocity having only the k hat component, which is what we mean by 2D. So here in this slide we are not restricting the point in any sense, but we are restricting the motion of the rigid body in some sense, that it's a 2D motion, not a 3D motion. So once this simplification is there, these can of course not help you with the first term, simplifying it in any manner, but the second term can be simplified quite a bit because of one term in r dropping off and two of the terms in omega dropping off, therefore the cross product becomes much simpler, and that's how you end up with just the moment of inertia times the angular velocity about k hat, and then of course the moment of inertia being defined as the integration of the sum of the squares, which in a polar coordinate will be even simpler, just an r squared that you would have in two-dimensional sense. So that's going to be multiplying your dm. Oh yeah, so of course this is something you're familiar with, that the notation that when we say subscript zz, it's about the z-axis and about the point P, that's you're taking the moment of inertia, which means that the k hat can be anywhere. If I introduce I, j, k at the corner of this room, I can actually translate that without rotating it to any point, without any loss of generality, because the origin is not kind of sacrosanct. You can have the origin anywhere. So that being the case, here you have to specify through which it passes. So therefore your z-axis has to pass through your point P about which you are taking the angular momentum. So your moment of inertia of Rb about the z-axis is passing through that point P, and therefore you have this simplification coming up in terms of the second term. Yeah, sorry.
About the notation again.
Yeah.
Or you have I P because it's passing through P,
Mhm.
it's easy because it's about the z-axis.
Yeah, which is why only the sum of x squared and y squared is there. For example, if it was ixx, you will have the y and z squared terms getting added up, and so on and so forth. Yeah, and if it is, it could also be a product of inertia. For example, xy, in which case you would have xy over here as a product instead of x squared or y squared, right? Clear?
Yeah, you just have the other variables.
Yeah. And for 2D motion, none of the other moments of inertia matter. This is the only thing which matters. and which is what. So this is essentially, if you're looking at inertia as a matrix, a 3 by 3 matrix, this is just the 3 component of that 3 by 3 matrix. That it's a diagonal term. It's the last diagonal term that you have on the principal diagonal, right? Okay. Next, again, we want to stick to arbitrary points, but now 2D motion. So that what would happen in that case? Okay. So I'll not go through the entire derivation because it's quite straightforward. It's one of the it's just combining 2 of the results that we already got. So essentially, this is what you end up with, very similar to what you had in the previous slide, except that the first term is no longer there, makes it much simpler. And this is the kind of problems most of the book will have for your textbook as well as in your homework assignment. So these are the equations that you would more often use. Okay, now there are certain tricks of the trade in terms of how you can actually simplify your workload in terms of solving dynamics problems, because almost every problem hereafter will involve the calculation of the moment of inertia. You don't need to do it from first principles always. Yes, it's a good exercise in integral calculus if you're of that kind and you like to go ahead doing that. So no problem with that. That's always the best thing. But why do something that has already been done? So it's kind of reinventing the wheel, which is why almost all your books give this as an appendix, all the list of these moments of inertia. So now there are certain problems which keep repeating quite often, and though you don't need to commit this to memory, it's interesting to see how this kind of arises. Okay, so you would when you're talking of rotating bodies, usually you will be dealing with either 3D bodies like spheres or 2D bodies like cylinders. Okay, so let's look at this. So you have either a sphere or you have a cylinder, and in either case it could be either solid, in other words it's fully occupied by material throughout, or it could be hollow, right? So now you have 4 options: a solid sphere, a hollow sphere, solid cylinder, and a hollow cylinder. And typically when we say cylinder, we typically refer to a thin walled cylinder. In other words, the thickness is very small compared to the radius of the cylinder. So we typically say a thin walled cylinder where T thickness is very thick, wall thickness is very small, the radius of the cylinder. Okay. Now recollect that your I is always going to be, of course, dropping the notations, assuming you're aware what we are talking about over here. So that moment of inertia for this particular problem, remember we start everything from point masses, particles, and for particles we say that if you want to take moment about a point, it's essentially the perpendicular distance, which is essentially your r squared times your mass of the particle. So it's an mr squared for a single particle, and it becomes a summation of mr squareds, mi ri squareds for a set of particles. We looked at that in quite detail last time. And then of course for a rigid body, once again the summation becomes an integration, and you also apply the constraint that the distances between any 2 points, any pair of points will always be the constant, right? So when we do that, it's quite clear that the end result of that, irrespective of which of these 4 cases that we are considering, will be kind of I will be proportional to mr squared, right? So because the total mass is going to come into picture of the sphere or the cylinder once you do the integration, that is, and then you're going to have the overall radius of either the sphere or the cylinder coming into picture. Okay, but depending upon which of these 4 cases it is, it's going to have a certain different constant of proportionality. That's the only way it is going to differ. In all cases, it's going to be proportional to the mass, it's going to be proportional to the square of the radius. Only thing is the constant of proportionality is going to be changing. Okay, so suppose we say that constant of proportionality is, let's say, some k times mr squared. It's very interesting to see what that k is for each one of these. You don't need to kind of remember that, but it's also important at least to know which will be higher, the highest amongst these four, and which will be the lowest amongst these. So for example, let's say 2 by 2 matrix, let me call it 1 1 2 2 the diagonal terms, and the first row, second columns 1 2 and 2 1. Okay, so out of these four, let's start with the largest, which could be the largest.
I had a question. Which axis are you doing this in?
This is about the z-axis. So essentially, you're talking about,
Like
let's say, yeah, let's say you have on the floor you have a ball, like what we were looking at a rolling problem earlier in kinematics. We didn't introduce kinetics there. So essentially, you're looking at this point about which you're taking the moments of inertia, because this is essentially a 2D rotation, and it has translation in the x direction, and I can make it a little more complicated, bring it this way, and this is now rolling down an incline. So now it has both x and y as far as translation is concerned, but rotation is only about the z, right? It's about the rotation axis is k hat. So whether it's angular velocity omega or the angular momentum, etc., they're all only going to have a non-zero k hat component, right? So that's the thing. So let me just, yeah, it's good to be precise. Okay. Yeah. It can rotate in many directions. That's why that 3 by 3 matrix is important. But here we are talking of a 2D problem wherein you're essentially dealing with all the quantities that you're interested in is your I, Z, Z, C. So essentially, for all these four cases, we are assuming the mass is the same, the radius is the same, the length of the cylinder doesn't matter. It's essentially calculated based on the masses being equal to each other. So you can always calculate the length based on the radius and the mass. So you essentially have that in control, right? Now, what is important is that the shape, whether it is sphere or cylinder, or in each case whether it is hollow or solid, it's going to make a difference as far as how large or small your moment of inertia is. And how large or small your moment of inertia is very important, because all of your things is essentially just like it's the same role which mass played here, your moment of inertia is playing over here. In other words, it's an inertial quantity. The very name says it all. It's trying to retard the motion. For the same kind of forces or torques in this case that are applied, you're trying to see how less an angular acceleration alpha that you can have, right? So in some cases you would want to reduce when you're designing a particular mechanism. Let's say you want to reduce the angular accelerations, you want to choose the geometry which has the highest I. In the other case, where you might want it to easily pick up angular acceleration, so you want it to go to from one speed to another, because typically these rotational motions get converted to translational motion, and therefore in terms of, especially for 2D problems, if you look at it, it's just a direct relationship that you have in terms of the V's and omegas. It just will have V is equal to omega R, etc., right? So your theta would similarly be your U is equal to R theta, or your alpha will be alpha R is equal to A. So for the simple case where you have just a 2D motion, so all of these will work. So this will, this is of course the simplest form in which you can have. The more, we know of more complex forms. We have already derived some of them, right? But now let's come back to this question. So depending upon, I would like you to say, let's start with the highest and go to the lowest. So which of these you think will have the highest moment of inertia, so that will kind of pick up speed much more slowly. So in other words, your accelerations are very low, angular accelerations.
Hollow cylinder.
Yeah? Hollow cylinder? Yeah.
Because,
Why? So you're saying this is the highest, right?
yes. Is it because so all the mass is centered out on the outside, so you have a greater mass?
Yeah.
And then next would be hollow sphere.
Mm-hmm.
And then
So
after
think
that,
hollow
solid
sphere.
cylinder and solid sphere.
Yeah. This one, third?
Yes.
Yeah. And fourth. Yeah. You're right. Absolutely right. Okay. So in fact, that constant K would be equal to unity for this. So in other words, you're essentially having 100% of your thing required. Of course, we are making some numerical approximations because we are taking t very small compared to r. If you calculate it exactly, it will be probably 98-99% depending upon the actual values. So, but essentially you're getting all your mr squared. Remember, we started off this from a particle equation. So that's what you would get for the particle. If all of the mass is concentrated at that distance, that's what your mr squared. So in other words, you're kind of recovering pretty much everything. That's why this kind of 100%.
Are we
Yeah.
assuming that the total mass of each of those are the same?
Yes.
Oh.
Yeah, yeah. So as I said already, m and r is constant for both. Okay, for all four cases. So the only thing we are looking at is how the geometry affects the inertia. Yeah. So yeah, so it's 100% of mr squared that you're getting. So what I'm actually plotting over here is, or listing out here is this divided by mr squared, right? So that's essentially what you're looking at, okay? So now the lowest is over here. So this is typically just about 40%. So you can see the huge difference that you have over there in terms of a solid ball. So if you look at sports, for example, the way you chuck a ball in different sports, quite different, starting with a shot put all the way, where you're looking at a solid ball, or most sports you'll have a hollow ball, and you see the difference in the way the ball's motion happens based on these aspects, because there is going to be a certain translational motion. There's also going to be a rotational motion, and sometimes these get converted one to the other depending upon, again, of course, whether the ball is in the air or it's on the floor, on the pitch, whatever. So then you are essentially going to get differences based on the kind of geometry that you have, and typically your this will be about 50%, and this will be about 67%. So this is kind of something that you don't need to remember the actual values, but at least in terms of which is highest and which is the lowest, if you have this at the back of your mind, it really helps when you're kind of designing either for larger angular accelerations or lower angular accelerations, which kind of geometry you would prefer, right? Okay, so now as I said, you don't need to remember all of these formula because they're typically given to you in textbooks and or the internet. You can always search and get that. Yeah.
67 is for the hollow sphere, and then 50% for the.
Yeah. Sorry. Yeah. Correct. Okay, as I said, you can get a lot of this information from textbooks, but they will give you only up to a certain level. It's not like your problem is already solved there, right? So it's for standard shapes about certain standard points, okay? Maybe the center of mass, maybe certain specific points of interest, like for example a cuboid at one of its corners, or something like that, right? So, or the center of a phase of a cuboid, whatever. So these might be given to you, but more often than not, your axis of rotation or some point or axis of interest might be somewhere else than what is given there, and that's where this particular theorem comes into picture, where this is again purely integral calculus mathematics, so we'll not go into the proofs of this, but we will just take advantage of what is listed, because this is something you would have most probably covered in high school math, if not physics, right? So parallel axis theorem, where we try to get the moment of inertia about any point, knowing it for about a particular point for the same body, right? So when you're doing that, typically you will see that, or rather by the very definition, you'll know that you can see that this is, if the point is the center of mass, you would have the lowest moment of inertia for that body. Any other point would be larger than that, and how much it is larger by is what this particular simple theorem gives you, and you will use it quite often. And also, though the book gives you or any books give you only for certain standard shapes, and most problems you would apply to are not standard shapes, as we discussed in the previous class on another context, most bodies can be thought of, realistic bodies can be thought of as made out of components which each of which are these standard shapes, and then you can kind of add them up, and then in that case again you'll use this parallel axis theorem, because you might want it about the center of mass of that realistic body, but you might be given values in the textbook for the centers of masses of those individual parts, the subparts, and then you have to transfer all of that to a single point which is common to the entire rigid body, which is your entire rigid body's center of mass. So this is the parallel axis theorem, and what it essentially says is that once you're given a distance between any two lines, it's called that distance as d, and this is parallel to the z-axis passing through P and C. This is a problem that can be used in 3D as well when you're interested only in the IISc term, but we are specifically focusing on the 2D motion, where this is the only thing that you're eventually interested in. But the same principle holds for any other direction as well. If you want to calculate, for example, Ixx and Iyy for some other problem where other motions or other rotations in particular are involved. So you would want to take care of that, or you might for some reason not, even though it's 2D motion, you might not want to introduce your k hat or z in the direction of the axis of rotation. You might want to introduce it in some other way, so you will have components. Then it might appear like it is not a 2D problem, though if you had chosen appropriate sense, it would have been a problem. So in all those cases, again, this becomes very, very critical, just a generalization of this, but we will look at just the z direction and Izz therefore, and therefore you have d squared is equal to the sum of the squares of, this is essentially your Pythagoras theorem. So you have xpc squared plus your ypc squared, essentially the distance on the x and y plane after you're projecting it onto those axis between the point about which you're taking the angular momentum and the moment of the translational momentum to get to the angular momentum. So essentially that's your P, and C is of course the center of mass. Okay, so then X. So it's of course whether you take it in whichever way, P to C or C to P doesn't matter, because eventually you're squaring it. So that's all that matters, right, as far as this is concerned. So now these two are related. So the moment of inertia in both cases is about the z-axis, but in one case it's the z-axis is passing through P, the other case the z-axis is passing through C. So now you want to correlate those two. As I said, this is the lowest that you can have about the center of mass. So any other point, arbitrary point, is just going to have a positive addition to it, and that positive addition is given by the mass of the body times the distance squared. So which is why this is called a parallel axis theorem, because those two lines are separated from each other by a constant distance, which is essentially what parallel lines mean. Okay, so this is something that you will use very often. This you'll just take from the tables that are there in books or in the internet, and this is something that you can get from the specific problem that you're solving. You just add that to get to a point P, and more often than not that point P that you would be interested in getting it is the center of mass of the overall rigid body made out of subparts, each of which are those standard shapes. Okay, now using the parallel axis theorem, many different ways in which this will be used for a lot of different problems. You'll actually see it when you're solving a lot of your homework problems. You'll be using this quite frequently. So we'll just illustrate one situation where we end up with an Izz about the C of the overall rigid body being that of the individual subparts that are making it up, and all summation over all of those subparts, and of course the summation over mi di squared. Okay, if you have to be a little careful, because in a lot of the literature there's something called the Einstein's summation convention, where any repeated index there is a summation over that. So here that doesn't hold. Even though you have a repeated index, doesn't mean you're summing over I, or here also you have a repeated I, but you're not summing over that. Okay, so but many books will kind of give you a simplified version where you will see that you are having that. So here we are explicitly writing the summation that you see over here, right? So whereas when you use the Einstein summation convention index, you don't need to put this sigma over here. It's understood that any repeated index, there will be a summation over it, and therefore you don't need to explicitly put the sigma. It reduces the length of your equations essentially. Okay. To find the moment of inertia in this case, so this is the end result. Of course, quite obvious how we arrive at that. So let's go through the steps to find the moment of inertia about the center of mass for any complicated rigid body which is composed of simple parts to it, simple shapes in the sense of that I'm saying simple parts. So then of course what you need is the mass, the location and the moment of inertia of each one of those parts. Okay. So because each part will have of course its own center of mass, you need to identify from a global coordinate where that center of mass is. For example, if to this very problem, if you are just attaching, let's say, something at the center, which is, let's say, a different here, which is attached at the center. So then you will have for the square or the cuboid, you would have some equation, and then for the cylinder or the cylinder you would have something else, and you would essentially go to the combination of that. Okay. So many problems it may not be, the centers may not be coinciding, so you need the centers of masses of each one of them. So these are the three quantities that are necessary, your MIs, the masses of each of those individual parts making up the overall part, DI, the distance of each of their individual centers of masses from a chosen reference, and of course in the xy plane, because that's what you are interested in, because the motion is rotation is only about the z-axis in this problem. So you have of course the moment of inertia.
So can you choose like some arbitrary point, like you have like some system of bodies, can you choose an arbitrary point and still do the parallel axis theorem to all of their centers?
Yeah, the parallel axis theorem always works, but you have to go one plane at a time. So you start with the xy plane to get to your IZZ. Similarly, you go to a YZ plane to get your IXX and so on.
Okay.
Yeah, it could be any arbitrary point. You're right. So these are the three quantities we need for each one of those subparts, and then you obviously see all of them are figuring in the final equation that you have over here. And so the moment of inertia of each part about the rigid body's center of mass, that is the overall center of mass of the entire structure. So essentially that distance is what is di, and then therefore that's applied to each individual part. For the ith part, this is the equation. Then you are of course summing up all of that to get the overall rigid bodies, because remember that y summation essentially, if you look at it even from the point of view of how we are defining it, it's essentially a set of particles, and you're summing over the set of particles which happen to be an integration. That integration is essentially broken up into a sum of integrals over simpler shapes. So that's essentially what you're having, and that summation still remains. The integration has already been carried out for you in your textbooks, and you're just using the parallel axis theorem to just relocate it to a different point about which you are interested in calculating the moment of inertia, because that's the point about which the angular momentum and the torques, etc., might be more natural to define for a particular problem. Okay, so this is the moment of inertia of the whole rigid body about its center of mass, the center of mass of the entire rigid body, that is. Yeah, Sid.
And could you replace the summation with the integral, and basically that's what you're going to do, you want to derive the...
No. Let's step back. So essentially, remember, of course you're free to interchange between them whenever you want, but if you remember, we started off with just a single particle for which we defined it as mr squared. Then for a set of particles we said it is mi ri squared. Then we summed over it, and now we dealt with not just discrete set of particles but continuous body. When you have a continuous body, you have infinite such particles, so therefore the summation automatically became an integral. Okay, so then you had your dm instead of your mi, and you still had your ri squared, which of course now is within the integral, so it goes to the left hand side, right? So it goes over here, right? So ri squared dm, this is over the entire body. Now you are saying you are going to a different case where you have a structure which is made out of many other structures, let's say like this. Let's say it's connected to a triangle in some sense somewhere there. So you have a rigid body which is kind of complicated like this. Let's say a robotics kind of an example where you have multiple rigid bodies which are in some sense linked to each other through some hinges or whatever. So now you are interested in calculating the moment of inertia of this overall system. When you are doing that, you are saying that instead of me taking any arbitrary point here and integrating each and every elemental mass dm over here in the same problem, it's going to become fairly complicated very soon. Okay, you already have the values for each one of these, so you take that from the book, and so now you're going back. So you went from the summation to the integration over here. Now you're going back from the integration to a summation, but not over infinite particles here. It's a finite number. In this case, in this example that I've drawn, it's just 3 parts, one triangle, one square, and one circle that you have there. So it's just summation. Okay, but for each one of those, your book has already done for you that integration. So it's essentially a sum of integrals, because summation and integration are interchangeable. Summation is when you have discrete nature, and the integration is when you have a continuous nature.
And when we do the summation, should we do it based off the center of mass?
Yeah, so see, it will be given for you in the textbook, it will be specified, you can actually look it up. Sometimes many good books will give you for more than one point, not only the center of mass, but probably other points which are typically, for example, they might not only give you for the center of mass of the triangle, but also the corners of this triangle. Well, of course, very easy to calculate once you have one, but instead of having you to do that, they might give it to you directly. So you take that, and then you look at the parallel distance, because this is in the xy plane. Whatever I've drawn over here is essentially in the xy plane. So all these distances will be the x squared plus y squared that we were talking about in a previous slide, and which is your r squared, and therefore you get your distance di for each one of those. So this will be d1, this will be d2, and this will be your distance d3, and then based on that, for each one of them you pick up the i's from these i's from the book, and then this summation is over 3 of those parts for the overall thing, and you end up getting this. Is that clear, sir? Yeah. Yeah.
So if you have like a system where, say there's like it's like a 4-bar, but like the object on the end of this is not rotating.
Okay.
So when you use the parallel axis theorem, do you negate the inertia of the object on the end?
No, all of them contribute, because if the rod itself is rotating, yeah, and this is on the tip of the rod, so it is contributing to the overall inertia.
Even if it's not.
Exactly,
okay.
Exactly, yeah. The very common thing is to see if you try. Yeah, so it's very similar to the moment as well. So if you have a momentum, if you're trying to lift a weight, if you're lifting it right here, it's much easier. If I try to lift it over here, because I'm now required to apply a certain moment, which is that weight times the distance, so it becomes more difficult, right? So something very similar to that is essentially happening over here. It's making it difficult to create the motion, which is what inertia is all about. It's trying to retard the motion. Right? Yeah, so I think this is clear. Let's move on. Okay, this is a radius of gyration. Is a topic that is very common again in a lot of your math. You would have probably looked at this concept. Here we will have more than one of them. So the plural of radius is of course radii. So radii of gyration is what we are looking at over here, and it's essentially coming from an alternate way of looking at the moment of inertia. Okay, so and this also is something that probably will be listed in a lot of your tabulations in the books and internet sources. So essentially this is something that can be used directly. If you know the mass, and the radius directly calculate the moment of inertia about the center of mass by multiplying the mass times the radius of gyration. In other words, the radius of gyration k is defined as I divided by m square root. Okay, so the square root of the whole thing is essentially what you're looking at, because so then you're essentially dealing with, in terms of instead of the actual I values, you're looking at it in the sense of how far it is in a inertial sense. So that's the measure of the radius of gyration. So it's essentially proportional to your inertia, but it's a geometric feature of the inertia. This is a feature of inertia coming from the mass. Just like translational motion, the inertial quantity was the mass. So that's also going to be the case with your rotational motion. But in addition, there's going to be a geometrical contribution. That geometrical contribution is very beautifully captured by your radii of gyration. And obviously, it's going to be different for different points about which you're going to calculate that. If for the same z-axis, if you choose two different points, P an arbitrary point and C the center of mass, obviously you know that IC is the smallest amongst all of those IPs, and therefore the difference, of course, is in terms of the parallel axis theorem, the mass times the distance squared between P and C. So quite obvious that the mass is not changing. The only reason they are changing is because your radius of gyration, the way you have defined it, is changing. So we are going to not only have this notation of k for the radius of gyration, but also depending upon about which point it is, we are going to put a subscript on that to say whether it is kc or kp, just like we had a superscript for the moment of inertia. The same quantity which went in point which went into the superscript for the moment of inertia is now a subscript for the radii of gyration. Okay, so mass distribution measures are defined in this particular way. So it's essentially, we are not talking of mass absolutely, which is also contributing to your inertia, but also how that mass is distributed, and which is why this difference in this tabulation came. In one case it was so large because that same mass m was distributed at the edges of the cylinder, whereas it was distributed all through the entire structure, much more compact. The volume would have been much enclosed by it would have been much smaller, but essentially you're having more material closer to the center of mass, which is not going to be of much use. So which is essentially what the difference is due to over there. And the same difference, of course, what we did for I, you can see the square root of those factors are essentially going to contribute to your Kc. So the difference may not look that big. So both these two radii of gyration, that is one about the center of mass and about the other about the arbitrary point, can obviously be related using your parallel axis theorem, because the parallel axis theorem relates the i's, that is the moments of inertia, but now we can substitute for the moments of inertia in terms of this, and all three terms now, including the mass times distance squared, parallel distance between those two axes, all of them had a factor of m, the mass, or the total mass of the rigid body. So the m cancels out, and it's purely a geometric relationship that you have now. This is another equivalent way of stating the parallel axis theorem, instead of in terms of moments of inertia, in terms of the radii of gyration. Once again, you see that Kc is going to be the least of the radii of gyration, and any Kp is going to be larger by this particular factor of d squared in a squared sense for the radii as well. Next, we will revisit the Euler's second law of motion again, but this time for 2D rigid bodies about a fixed axis. Okay, because 2D already we know that it's a motion which is taking place where there's only one rotation about a particular axis, the z-axis, and about which you have the unit vector k hat, and therefore about that any point on the fixed axis. Remember that this is valid about a point, but that point could be on the axis is what we are essentially saying. And this is in some sense kind of similar to what we have talked about earlier, because it's an axis which is fixed both in the inertial frame of reference and on the rigid body, but in particular for the 2D case is what we are looking at over here. So for 2D rigid bodies rotating about a fixed axis, which is what 2D motion is all about, you can identify that axis, and even if that axis is not passing through the center of mass, because you don't need the axis of rotation always passing through the center of mass. It could be rotated about some other points. For example, I could take this and hinge it over here and then rotate it about my finger. My finger is the axis of rotation for this object. So it's not, of course, passing through the center of mass. If it's uniformly distributed, then you know that it's at the center of the length, breadth, and the thickness of this cuboidal shape, and then you will not have it passing through the center of mass. So even in such a situation, any arbitrary choice, except that it has to be on the fixed axis, then you would have the moment equal to the sum of the moments acting on the on that particular rigid body. Of course, all the moments will be about the z-axis, just like your angular momentum and angular velocity, angular acceleration, the angular displacement are all going to be about the z-axis. That's what 2D motion means. We already restricted the problem to that. Then obviously you can drop off many of these subscripts. Truly speaking, I should have had, for example, alpha z over here. I'm not mentioning that because that's the only alpha which survives, which is non-zero, and therefore you have that. And similarly your omega, I can write it as just omega dot, though I put z over there, then that's the theta double dot that you have over here. So you can very clearly see that the only thing that is changing is, of course, the angular way in which you are describing the problem. One case it's an acceleration, in other case it's a time derivative of the velocity, and the other case it's a second time derivative of the rotation itself. And all of them, of course, the inertial baggage that you're going to have, just like the baggage was m over here, the baggage here is your IZZ about the point, arbitrary point P, but fixed on the axis. So now we're kind of done with that. Now we'll get into another topic, which is essentially an application of whatever we have talked about today, and also parts of what we talked about in the previous class. So now we are going to revisit this. But remember that we talked about rolling and slipping earlier too, when we are talking about kinematics. Now we are going to extend that problem a little more to kinetics. The cause of the motion is also now within our grip in terms of handling it. So we can introduce those causes in terms of the torque, and we can talk about the moments of inertia, etc., to set up the problem entirely. Earlier we were only connecting the displacements and the angular displacements and its derivatives. So now we are able to do something more. So now we can also there mostly we are talking of something rolling on a flat plate, horizontal, but now we could incline it, and things will become a little more interesting. Some things which seemed trivial in the previous problem will now become more interesting. So as always, we'll start with an inertial frame of reference. You have your, let's say, we'll use this as the z, so x and y will use this. So your I hat, not require all of them because we're going to restrict it to a 2D motion, but for completeness. Okay, now we start with an inclined plane. And we start with a body. Because we are going to be dealing with only 2D bodies, should I restrict this to a cylinder, or can I still have a sphere?
They have different modes of inertia, so
Yeah.
you can just choose.
Yeah. So as long as the ball or sphere rolls in a plane, it doesn't kind of move out of a plane. So you could still use the 2D motion. So it's not necessary that this be a cylinder, it could be a sphere as well. And of course it can be solid or hollow, doesn't matter, right? Only thing that is going to change is that factor k in your kmr squared to calculate your moment of inertia. Right? So now this is your body, then let's say the mass is uniformly distributed in it, irrespective of whether it is solid or hollow. With wherever the material is there it is kind of constant density, so its density is not changing from one point to the other, right? So it's made of the same material, let's say. So then you let's say we have the radius of this to be r. Okay. So now what are the forces which are acting on this?
Weight.
Yeah, so that's vertically downwards, your mg.
Normal.
Yeah, so this mg can be looked at as its components, and so which of these is mg sine theta, which is cos theta? This one is?
What's theta?
Yeah, good question. That's brilliant. Let me not use theta because we'll probably use theta for that rotation angle over there. So let me call it beta. Yeah. Alpha is already taken for the angular acceleration. So yeah.
With a sine wheel.
A sine would be the one going down.
Yeah.
Yeah.
And then cosine would
Yeah.
be one going
So then Kush mentioned the normal force. So that's essentially to take care of this mg cos theta, and so that's essentially coming over there. So equal in length to that. So let's call it n. So right away we are utilizing one of the equations of equilibrium of forces. That's the yeah. So this is inertial frame. I can introduce a frame in which the x and y are along this. Okay, let's say capital X and capital Y, uppercase. So then z of course is the same in either one of these cases. So this I can write it as this, and z is coming out. Or you can also think you're familiar with this notation. I saw many of you using this already. So arrow coming out, so it's essentially what you have as your z direction, right? So now your n of course is calculated by a summation of forces in the y direction. So summation of Fy equal to 0 gives you n is equal to mg cosine beta. So
You assume friction force.
yes, yeah.
So there would be a friction force pointing up the hill.
What will happen if it is frictionless?
It'll just slide.
It'll.
Yeah.
The friction allows it to roll versus just to slip down.
Good, yeah. So if the friction is there, so how or in what direction will it act? Yeah, because the motion is going to be downwards, because that's what the mg sine beta term tells you. So therefore, obviously, it's going to be in this direction. Okay. Now, what will be the value of that in terms of the quantities already listed? Yeah. Is it kinetic or static? Mu S or mu K?
If you're rolling, it's static. But
Wait,
if the
oh,
friction is
shoot.
high enough that it's just there.
Wait,
it's
can you
static.
repeat that? So one second. So it's static if it's not.
If it's rolling, then shouldn't the direction of friction force acting change?
Yeah, it should be the other direction, right?
Wait. So
If it's rolling because the
Was that the next thing that
Yeah.
you're going to
It's okay.
That's what I was wondering. I was like, wait a minute.
please don't. Wait, I'm a little bit.
Yeah, that's good.
What?
Yeah.
Okay, wait. First, I want to talk about if it's static or.
Yeah.
So, since it's rolling,
Uh-huh.
it's not. That point is like fixed.
Yep. Yeah, we studied that already in kinematics, right? Yeah.
So it's static,
Yeah.
and because it's rolling that direction.
Yeah. So let's write that mu S and
So it'd be mu s times the normal force.
yeah.
Okay.
Yeah.
Well, it's in the opposite direction.
But it's in, why?
The reason why is because at the bottom of the ball, at the contact point, the ball, the instantaneous velocity is going up the hill actually, since it's rolling down the hill. That means the friction has to oppose the direction of the instantaneous velocity, which is the friction will point down the hill.
Okay, so if it is slipping, what happens?
If it's slipping, then there's a component that's going up the hill.
Yeah, so this is right if it is slipping, right?
Yes.
So we are going to consider all possibilities. So including frictionless state, we are going to look at the, let's say, where there is friction and whether it is rolling, pure rolling, or we'll look at slip. And so all of these things, subtleties in terms of how it changes will happen. Now what is the role of...
But if it is slipping that, and then we define the frictional force, then won't there, because of that frictional force acting on the ball at like a point, like the force itself will cause a rotation, right?
Oh, you mean it's gonna push it forward because of the rotation? I don't know if that.
Or not,
makes, like,
not that, like,
If it's slipping,
yeah.
then what are you asking?
So if we define mu s times n to be the frictional force going up the hill, and that's when it's slipping, correct? Wouldn't that frictional force itself cause a rotation?
Exactly. So
Yeah, that's why it rolls because of the friction, right?
see, for any rotational motion, including rolling, you need a torque. Okay, torque is just like for translational motion, you need a force. For this, you need a torque. Okay, so the torque has to come. It cannot come from your mg, either one of these, because it's passing through the center of mass and the axis of rotation, right? So it cannot come through mg, it cannot come through n. N is also acting through the center of mass and the axis of rotation, right? Now, the only thing which is having a moment arm is your frictional force, and that's something that can cause rolling. So what is the direction of the torque required and the rotation? Should they be same or should they be opposite to each other?
Well, doesn't the friction oppose the motion that's on the diagram? So
When you ask the direction of torque,
Yeah.
maybe like the K is negative K.
Yeah, it's either clockwise or counterclockwise.
Yeah, see, when I want this to move in a particular direction, I have to apply force on it. It's quite obvious I have to apply the force in the direction in which I want the motion, right? So now I want this to roll.
Oh.
Okay, so
To the page if you want to roll clockwise down the road.
yeah, but
Like clockwise if you do R cross that.
oh,
If you assume the friction force
okay,
is going
okay, yeah, because like this. Yeah.
but don't forget that there are two of these mu s n acting on the ball and that of acting on the road.
That's what I was getting at.
That's where his conundrum comes into picture, right? So, and which law tells you how they're related to each other? Newton's third law, so equal and opposite reaction. So whatever forces are exerted by the incline on the rotating body, the opposite will be by the rotating body on the incline, right? So both those forces will actually be there. So in both, which obviously since they're opposite, they will always be opposing each other. So which is happening on what is the question. And for this rotational motion to take place, if rotation has to happen, rolling, then you have to have a torque. And just like for the motion, translational motion, the force has to be in the direction of in which you want to increase the velocity. Similarly here, the direction you want to increase the angular velocity. So that's angular acceleration is related to your torque. And so it has to be the way the incline acts on the body, it has to be this particular way, right? So that's the only source of torque. All the we already saw are passing through the axis of rotation. The only place that is that, right? So what is essentially the difference between when it would slip and when it would roll is to a large extent determined by your mu s, how large or small it is. What happens when it is fairly large? So It was talking of relative terms.
Rotation will be more, so
Yeah,
then it
yeah.
will start slipping.
The possibility of rotation is more. So there are gradations. So we start with frictionless where mu is 0. Okay. So then you know that it's going to slip. The reason why you skid when you're going on an icy road is essentially that the coefficient of friction has come down. So between your tires and the road, right? So that's the reason why you're skidding, right? So same thing, whether it's on an incline or on a plane, you're essentially saying that that is going to happen when the friction is not sufficient. So frictional force is not sufficient. Okay, so that's essentially. So you start with 0, you go with lower values, then you go with little higher values, and so on and so forth. So we will try to do that. How many minutes into the video?
1 minute.
Okay, probably have another 5-10 minutes. Yeah. So before that, of course, yeah. So if it's on an incline, or even if it's on a even before an incline, when you have beta equal to 0, it's a flat plane. You could, of course, be pulling that body using ropes, strings, cords, or you be driving using an engine or motor. So whatever. So essentially, you have all these possibilities in terms of gears and chains and how you actually do it, and it need not be about the overall radius. It could be about drive could be on a smaller radius or a larger radius, depending upon the leverage that you want to get. So now we are focusing on this, and we can look at this as a special case when it's on a flat horizontal plane, beta equal to 0. So now we have the 2D rigid body equations of motion. So these 2D rigid body equations of motion, the dynamic equilibrium equations employing resultant forces and moments acting at the center of mass. So it's essentially an extension of what you have already done in statics, except that the right hand side, instead of being 0, is going to be equated to mass times acceleration for the forces, and to inertia, a moment of inertia that is appropriate direction with the angular acceleration alpha, also about z, because if we are looking at 2D without loss of generality, we'll always take the rotation about k hat, which is parallel to the z axis. So now it's very easy to see that though a rigid body has 6 degrees of freedom and therefore 6 equations of motion, 3 of them are trivial. They all just go to 0. In fact, in our case, we saw even one of the others went to 0, which is perpendicular to the path of the incline, where we just said there's no acceleration because there's no motion in that direction, just equated the forces like we do in statics, right? But the other 2 are important for us. Yeah. So the other 2 are important for us. So in terms of the x direction translation and in terms of the rotation about the z axis. So that's where this comes into picture. So now this is of course an application of Newton's second law, where you're just saying that the force is equal to the mass times the acceleration, and in the simplified 2D problem, the moments are equal to the rate of change of angular momentum, which is equal to moment of inertia times the angular acceleration, which you can put in terms of all of them. Instead of putting in terms of accelerations or velocities, we are putting it in terms of the displacements, both translational displacements and the angular displacement, your theta, and therefore you have double dots coming up from each one of them. So this is how we progress from Newton's second law, which is what you see over here, but even that was extended by Euler to the rigid body when he took them not as a concentrated mass, but essentially spread out, distributed, and therefore you have the Euler's first law. But this is much more of a novel contribution in terms of your second law relating the moment to the angular acceleration. So this very clearly, as we already mentioned, is a 2D vector equation as far as translation is concerned, and just a 1D scalar equation as far as the rotation is concerned. So we take advantage of that. Now coming to the forces on rolling or slipping, as we already saw the table that we had in terms of hollow or solid, cylinder or sphere. Okay, so those are the 4 cases we had, all the way from 40%, 50%, 67% to 100% of leveraging your mass times the radius square, the radius being either of the sphere or of the cylinder. So that's essentially what you're trying to do. So irrespective of whether it is rolling or slipping, some of these forces are anyway there, like the gravitational force, for example, mass times the acceleration due to gravity, right? So that is always there, and the resultant by definition of the center of mass acts at the center of mass. But if you have a very large body in space which is affected by more than one gravitational field, it is possible that the center of mass and the center of gravity are different from each other. So center of mass is purely a property of the body. Center of gravity is a property of the body as well as the field in which it is. Okay, so the gravitational field, if it's going to vary from point to point on the body, a very massive body, let's say, or for example, you're doing it on a planet or a satellite, etc., then you could have natural satellite that is fairly large. So then you would have to take that into account. But right now, we can use it interchangeably, whether it's center of mass or center of gravity, right? So in reality, what is happening is that this is a mathematical simplification that we are doing, that mg is acting at the center of mass. In reality, each and every infinitesimal element at point q that we were talking about, with notation that we introduced, that bm times g is what is acting as small forces, all of which are getting integrated to your overall mg, where m is the total mass. So it's a distributed gravity load, is statically equivalent to a single force, and the static equivalence you would have seen in terms of calculating resultants in your statics course already, single force at the center of mass. Now coming to the forces on the rolling or slipping solid or hollow cylinder or sphere. So we are combining all of these kinds of problems which are typically posed as individual problems in the bigger picture to see that all of these can be considered in the same paradigm, and then all that you have to change is that factor k in your k mr squared, and then everything becomes quite straightforward. Okay, so you can solve it for just an arbitrary k, and then you can substitute for the k values towards the end, and all four of your problems are solved simultaneously. Okay, but we now have an additional complication in terms of whether it is rolling or slipping, and these kinds of things that we just discussed, we will have to see. And of course, the angle of inclination all the way from 0 to a positive value. The very interesting trivial case again would be when it's a vertical path that it has to go down by. Sometimes that can be applied for pulleys. When you're having something on a pulley and then a load is coming down a pulley, it's essentially traveling vertically, but it's not rubbing on any surface. But you can also have it moving with rollers or whatever on a path as well. So essentially you can introduce some of these concepts into such problems as well. So it's essentially the methodology that is of more of interest to us. Okay. So I'll stop with this slide, and then we will continue after lunch. So normal reaction, of course, is the first force. Krish already mentioned over there, that's always going to be perpendicular to the surface at the point of contact, and the contact may not be a point. In the case of a sphere or a solid or hollow, it is a point, but in the case of the cylinder, it's a line. It could be any kind of a contact surface. So the interesting thing is, many of the results, both intermediate and final results, will not differ based on whether it's a point contact or a line contact or a surface contact. In fact, many things will not even be a function of the total mass or even the radius of the sphere, but that factor k will always come into picture. So that's even more important in terms of distinguishing different problems. K plays a much bigger role than even m and r, because they tend to get cancelled out for a lot of the results that we are interested in. We will see that shortly. Okay, so whether it's a horizontal plane or a inclined plane, you see it's always perpendicular to the plane. And just like in the friction force, we discussed Newton's third law, equal and opposite. Here also there's an equal and opposite. So this is the force as shown here. Is it being exerted by the rod on the ball or the ball on the rod? Yeah. So obviously the other one will be opposite in direction, equal in magnitude. So that's not of interest to us, because we're not worried about what happens to the road, like very good citizens, and we are interested what happens to only our wheels of the car. So the normal reaction, of course, acts at a line, a point of contact, as is the case with a cylinder or a sphere, and acts perpendicular to the contact plane as is shown in this picture, and calculated using, of course, just static equilibrium, because we saw there's no acceleration or no, in fact no motion at all. The y displacement, the y double dot, y dot and y double dot are all equal to 0, and therefore just a statics equilibrium equation of summation f y equal to 0 is what we could apply over there, because there's no motion or dynamics in that direction. Okay, so of course, yes, normal means perpendicular, so we will continue with this after lunch.
Is it possible to get some force in that direction, or is it always
Which direction?
the normal direction, the normal force direction, like the y, or is it always? Is it possible?
The force is there. The motion is not happening because it's getting balanced out. There are two forces acting. One is a component of the gravity and mg cos beta, and the other is n. They are equal in magnitude to each other, and therefore there is no resultant force, and therefore there is no acceleration in the y direction. You're asking, can there be a acceleration y direction, right?
Yeah.
I mean, you are an aerospace engineer. You don't just drive on roads, right? You have to take off.
Yeah.
So when you take off, where is that coming? Yeah.
Exactly.
So you're essentially your lift. So your lift is
I was talking
your-
like in these examples, but yeah,
Right.
obviously, yeah. When you look at a
Then we
car,
don't have to study rolling. We can
that's
just
and in the y direction, they don't. That's where the acceleration comes from. You have the force of the weight,
Mhm.
and then you have the load.
Absolutely, yeah.
That makes sense.
Good.
So the cylinder, if it was an airplane rolling down,